Hello everyone, I am Dr. Navneet Kaur from Department of Electronics and Communication Engineering, Sagar Institute of Research and Technology College. Today I'll be taking lecture on subject optical fiber communication, which is having subject code EC801. Now, to start with, I'll be taking the topic ray transmission theory. Now, first, we will understand what is fiber optic communication. Now, fiber optic communication is a method of transmitting information from one place to another by sending light wave through an optical fiber. This light wave forms an electromagnetic carrier wave that is modulated to carry information. Now, what is an optical fiber? Optical fiber is a dielectric waveguide that operates at optical frequencies. And this fiber waveguide is normally cylindrical in form, in which the signal is propagated in the form of a light wave. Now, what is the function of this optical fiber? It confines electromagnetic energy in the form of light within its surfaces and guides the light in a direction parallel to its axis. Now, to start with the ray theory, first we will study laws of reflection. Now, we have already done laws of reflection in our previous classes. Now, to recall these law of reflection, now suppose I have any reflective surface. Say I have some mirror whose one of the surface is reflective and other surface is coated. Now, when a light ray is incident on this reflective surface, the part of the light is reflected back. Now, this is the normal, and the angle between the incident ray and the normal to reflective surface is, say, phi1, which is known as incident angle. And the angle between the normal to reflective surface and reflected ray is phi2, which is known as angle of reflection. Now, according to the laws of reflection, this angle of the incidence phi1 should be equal to the angle of the reflection phi2. And the second thing, that the incident ray, the normal to the reflective surface, and the reflected ray should lie in the same plane. Now, what is refractive index? Refractive index of a medium is defined as the velocity of the light in air or vacuum to the velocity of the light in the given medium whose refractive index is to be calculated. Now, according to this equation, it is clear that if the refractive index of the medium is high, that means the velocity of the light in that medium will be less. Whereas if the refractive index of the medium is less, the velocity of the light in that medium will be high because the speed of the light in air is fixed. It is constant at 3 is to into 10 is to power 8 meters per second. Now, the amount of refraction or bending that occurs at the interface of two materials of different refractive indexes is usually expressed as the ratio of the refractive indices. Now, refractive index is also known as index of refraction, and it is generally denoted by N. Now, refraction occurs when the light ray passes from one medium to another. Now, since the refractive indices of both the mediums are different, the light ray changes its direction at the interface of the two mediums. So, refraction occurs whenever density of the medium changes. For example, suppose we have two mediums, one is air and another is the water. Now, at the air and water interface, when a light rays comes, it will change the direction when it passes from air medium to the water medium. So, the straw or pencil in a glass of water will appear always bent. Now, Snell's law. Snell's law states how light ray reacts when it meets the interface of two media having different indices of refraction. Now, suppose we have two medias. Say one is having refractive index N1 and another is having refractive index N2. And N1 is greater than N2. Now, phi1 and phi2 is the angle of incidence and the angle of refraction respectively. Now, this can be shown in this figure. Now, these are the two mediums. One is having refractive index N1 and another is having refractive index N2. Now, this is the light ray, which is incident ray and is making an angle of incidence phi1 with the normal. Now, this light ray is refracted into the second medium. Now, here we can see that the light ray changes its direction when it comes into the second medium. It is not taking the straight line, rather it is bent when it is moving into the second medium. Now, the angle between the normal and the refracted ray is the angle of refraction, which is denoted by phi2. Now, according to Snell's law, N1 into sine phi1 is equal to N2 into sine phi2. That means N1, which is the refractive index of this medium, into sine phi1, which is the angle of the incidence, is equal to N2, which is the refractive index of the second medium, into sine of phi2, which is the angle of the refraction. Now, Snell's law will equate these two terms. Now, if I take N2 on the left-hand side and psi phi1 on the right-hand side, I'll get equation N1 by N2 is equal to sine phi2 upon sine phi1. Now, if N1 will be less than N2, in that case, phi2 will be less than phi1. That means phi2 will be less than phi1. That means this angle will be smaller than this angle. In that case, the light ray will move towards the normal. So here we conclude that if N1 is greater than N2, which I have followed from this equation, if N1 is say less than N2, then phi2 is also less than phi1 because this is constant ratio. Now, in that case, N1 is less than N2. That means N1 is a medium of less refractive index. That means it is rarer medium and N2 is a denser medium. So, when light rays move from rarer to denser, the light will always bend towards the normal because here phi2 will be less. Whereas, if N1 will be greater than N2, to maintain this ratio constant, phi2 will be greater than phi1. Now, if phi2 will be greater than phi1, that means this angle will be increased. Now, in that case, the light ray will bend away from the normal. So, here we conclude that if N1 is greater than N2, that means N1 is a denser medium and N2 is of a rarer medium. So, when light travels from denser to rarer, the light will bend away from the normal. Now, say I have incident ray which is making an angle of incidence phi1 with the normal. Now, if I'll go on increasing phi1, now in that case, the angle of refraction will also go on increasing. Now, if this angle of refraction will go on increasing, this light ray will now be shown parallel to this interface. That means this angle of refraction will now be 90 degree. So here we have seen that when angle of incidence will go on increasing, it will reach a point where this angle of refraction will become 90 degree and this light ray will be shown parallel to this interface. Now, this point of angle of incidence is known as critical angle. So here we conclude that at critical angle, phi 1, say it is denoted by phi c, this angle of refraction will be 90 degree. Now, if I will increase this angle of incidence beyond this critical angle, in that case, the angle of refraction will be more than 90 degree, and this refracted ray will be shown in the first medium only. That means in that case, the light will not be propagated in the second medium. Rather, it will be propagated back into the first medium only. So, this angle after which the refracted ray will be propagated in the same medium is known as the critical angle. So, using Snell's law, n1 sine phi 1 is equal to n2 sine phi 2. Now, when phi 1 is equal to critical angle, say phi c, in that case, phi 2 will becomes 90 degree. So, n2 upon n1 sine 90 degree. We know sine 90 degree is 1. So, sine phi c will be n2 upon n1. So, critical angle will be given as sine inverse n2 by n1. This is the equation for the critical angle. Now, we have already discussed that when the angle of incidence will be increased beyond this critical angle, then the angle of refraction will be increased beyond 90 degree, and the light ray will be propagated into the same medium. Now, this forms the principle of the propagation of the light in the optical fiber. Now, this principle, this process is known as total internal reflection of the light beam. So, the total internal reflection process leads to the propagation of the waves within fiber cable medium, because here the fiber will be made up of the inner cylindrical medium, which will be known as core, which will be having, say, refractive index n1, and it will have outer cylindrical medium cladding, which will be having refractive index, say, n2. So here the angle of incidence will be beyond critical angle, so that the light ray will be confined to the core only. It will not be refracted into the cladding medium. Now, this will be shown in my further lectures in detail also. Now, the two conditions which are essential for total internal reflection to occur, which we have already discussed, that the refractive index of the first medium must be greater than the refractive index of the second medium, and the angle of incidence must be greater than the critical angle. Now, this is all for today's lecture. In my further lectures, I'll discuss more parameters of the ray theory, and we will study in detail the structure of the waveguide and the propagation of the light wave signal in the waveguide. Thank you.